Hello, my children of AP Calculus AB. I am missing you all. Somehow I'm missing 7:45 in the morning seeing your smiling faces. But we're working on slope fields in section 10.1. We've got one unit to go. The AP peeps will have more information out about the test this Friday. So I'll be able to tell you more about your options and how we're going to proceed. But for now, they're saying we need to learn one more section of things, and that's where we are. So I'm looking at the problem. You watched the video already from section 10.1 from Flip Math. And now I'm going to give you a few pick and choose problems along the way to help you with the practice. So the first one I'm looking at is number 4, because you guys all tell me you hate the trig functions, and that's probably the one you would pick. But I love the fact it's got a little calculator next to it. So what I'm going to do is they want me to draw the slope field for each of these differential equations. Remember, a differential equation is just telling you it's the derivative. Derivative equation is the cosine of x. So all I need to do is go into my calculator and put in the cosine of x into my y equals. And it's all dependent upon just the x value for this one. So this one's relatively easy in that thought pattern. But if I go to the table, and in the table I put in, let's start with -2. If x is -2, what's the slope? And the slope is a -0.4. So what I'm going to do is everywhere that x is a -2, I'm going to put in a slope of -0.4. Again, you're just kind of estimating, it doesn't much matter. Next one I come to is when x is -1. If x is -1, oh, I get a positive 0.5. So I'm going to make a positive slope at all of these guys. Next one is if x is 0, I get a slope of 1. That's also positive, so make it a slope of 1. If x is positive 1, I get a slope of 0.54. So again, it's going to be a positive, but not quite as steep as this guy. And then I'm going to say a slope of 2, or when x is 2, I get a slope of -0.4. Now I'm back to the negative part. So here it is, negative slopes of 0.4. And that, my friends, is your slope field. So that one was really relatively easy if you just use your calculator. So the second set of practice problems has you matching. You're trying to match each of these differential equations with each of these slope fields. And so the first one I have is number 7, and I'm looking at my 4 options. And remember, these are like cattle chutes that if you were to stay within the cattle chute, you'd be drawing the actual function. So I'm looking at these cattle chutes and deciding does that look like a sine function or not? And I'm like, I don't think so, because if I were to trace in between there, it would kind of go off like this. If I were to trace this one looks like a parabola. If I were to trace this one, oh, maybe that might be, right? It's kind of going up and going down and going up and going down. That might be a sine function. If I come to this guy, he asymptotes like this. So the only one that makes sense for number 7 is C. And that takes this one off the mark. If I were to graph the graph staying in the cattle chutes of this one, it would look kind of like this, which looks a little like the sine graph. All right, let's take the next easiest one, number 10. Number 10, the slope is x. So the question is, when does the slope equal 0? And the slope equals 0, this is the slope, this is your x value, when x equals 0. So of my remaining places, which guy has a slope where x equals 0? Anytime I have an x of 0, I have a slope of 0. Slopes of 0 are horizontal tangent lines. This one is already out of the loop. This one wouldn't make sense. This one wouldn't make sense because along the 0 it changes slopes. This guy has to be the only one where your slope, every time your x is 0, your slope is 0. Also, if you think about it, if your x is 1, you have a positive slope. If your x is -1, you have a negative slope. So B is your deal for that. For the next one, that leaves us with A and D. And so if I look at the next one, let's see, the next easiest function might be this guy. When would this slope equal 0? Slope equals 0 when 0 equals 2 minus y. And if I were to solve that, when y equals 2. So which one has, when y equals 2, slopes of 0? Is it A or is it D? If I look at that, slopes of 0, oh, check him out. The slopes are 0 at 2 because I've got horizontal tangent lines at that place. So this guy would be my A, and by process of elimination, this guy would be my D. You can double check it. This one's saying that when you take the x coordinate and subtract the y coordinate, that's going to be what your slope is. So if I take x minus y, 0 minus 0, 1 minus 1, 2 minus 2, 3 minus 3, my y values and such to up the line, x and y's. So there's matching and kind of how you get around the matching things. Then you come to, next one I want to do, all the ones on the next page are fine, but number 19 I think is a little bit challenging, so that's the next most challenging one that I see. It says you have a differential equation that is x minus y, which is actually your number 8 from the problems we just did. Same differential equation is x minus y, and it says, all right, you got the slope field. State a point where dy over dx equals 0. All right, let's take it one thing at a time. So I want dy over dx equals 0. In other words, where is 0 equal to dy over dx equals 0 when x minus y? And so I'm looking for state a point where that happens. Well, if I solve this differential equation, I get y equals x. So that means that my y coordinate and my x coordinate have to be the same. There's lots of places that that happens, but let's keep it simple. If my x is 1, my y is 1. If my x is -1, my y is -1. If my x is 2, my y is 2. I could pick a lot of different choices for points where that happens, but my point is going to be the point 1, 1. And I can even be more specific to say where dy over dx equals 0. So state a point where that happens. There you go. Then it says, all right, find the second derivative. That's a funny notation for second derivative. It says find the second derivative and use it to verify if your point is a maximum or minimum. All right, well, if I think about that, I'm going to come off to the side here and show you the work for this. This is saying that my first derivative equals x minus y. And then I have the second derivative it wants me to find. This is implicit. Remember back to the days of implicit, right? So my second derivative is going to be take the derivative of an x, derivative of x is 1, take the derivative of y, that's y prime, but I need to say that that's my derivative. Remember I took the derivative of something, it really would be 1, but it's 1 times my y prime. This is when we had colored pencils, you remember back in the day. All right, so I'm going to do some substitution, see if you can follow this. I have a 1, I have a minus, but guess what this is equal to? My first derivative, which is this. So that's going to equal x minus y. And so if I find my second derivative like they asked me to, it would be 1 minus x plus y, and if I distribute through that negative. That's my second derivative. That's the d squared y over dx squared. But I'm not done because it says, all right, find it, but that's not good enough. Use it to verify if my point is a maximum or minimum. Well, the point that I chose was the point 1, 1. So let's plug it in and see. Second derivative, 1 minus 1 plus 1. Look at this, it's calculus, right? And our answer is 1. If my second derivative is positive, that tells me my concavity is concave up. So if it's concave up, then I know that this must be a minimum point. So I have a minimum at 1, 1 because my second derivative is positive or concave up. So all of that is verify that we've got a max or min, we've got a min because it's concave up, second derivative positive. And then part B says, sketch the graph of a particular solution of the differential equation that contains the point -3, -1. So let me find -3, -1 is in this vicinity. So you locate that location, and then really honestly, you just stay between the cattle chutes. There you go. See if I can twist this around. I'm going to go up like that. It's an estimation, kids. It just has to be something that looks something like that. Doesn't have to be anything too crazy. Okay, so there's number 19, and I think that's enough example problems for you to do the rest of those, and I will talk to you soon. Miss you guys. Bye.